Só para avisar o pessoal que está vendo de casa online, como eu conversei aqui já com o pessoal que está aqui, essa quinta-feira não vai ter aula. Semana que vem vai acontecer uma conferência aqui, entre o dia 5 e o dia 9. Depois vai ser o carnaval. Então é assim, a última aula dessa semana vai ser na quarta-feira e depois as aulas retornam dia 15, tá? Só para vocês saberem. Okay, so let's go back to what happened yesterday. So we defined. So yesterday we started the definition and the construction of the contours for the long-range ferromagnetic Ising model. So what we did is to introduce a definition. So we called the MA delta partition. The MA delta partition for a finite set from ZD is defined by it's a collection of subsets, okay, collection of subsets of ZD, finite subsets of ZD that satisfies two conditions. So the first one is one that is called the A condition, and it means that it asks gamma A to be a partition of A. So this means that they are disjoint when I is different from J, and their union is the whole set, okay? And also they satisfy another important condition if so given moreover, so given gamma I, gamma J different elements, distinct elements, then there exists an unique connected component of the complement of gamma J, okay? The complement of gamma J, such that, let's say, a unique component C of the complement of gamma J, such that gamma I is contained in C. Okay, so again, I will make some drawings to make this point clear. So if I have some set like this, and I want to make like a mask, okay, a mask with some I want to make a partition like this. This is gamma 1, the yellow part, and this is gamma 2. This of course forms a partition of the set, but does not satisfy condition A. Why? Because the complement of gamma 1 is the black part of the blackboard, and what I have is that I have three connected components. So I have this connected component, the connected component of the interior, the whole board, the whole blackboard. I have this connected component and this connected component, this one, okay? So in order to this drawing, to this partition of the set to satisfy condition A, then we must separate the two green sets to another different different element of the partition. So okay, this is good, but it's not the whole story. We need also another condition that separates the elements in the following way. So there is a condition B that says that, again, for any pair gamma I gamma j elements of gamma A that are distinct, okay, we have that the distance between the two sets is larger than m times the minimum of their volumes gamma j to the power a d delta. Okay, I said I called this M a delta partition because when we define this, we need to fix three positive real numbers, okay, in a way that this makes sense. So this it's where the information of the M a delta partition comes from. And what this is saying is that if some part of the set has a volume that is too large, then it cannot be close to what this means is that there is a you cannot be too close from other components, and the distance actually depends on how massive is the element of your partition. So when the volume so if you want to try to, if you have some small component right here and you have a large component right here and you want to approximate them and still have an MA partition, then what this condition is saying is that you cannot be as close as something that depends on the mass of this smaller component. So, okay. Just to get a sense of what's going on. So, okay. What I want to tell you is that first, we only consider the case delta equals d plus 1 because this is the this works for all the calculations that we will do. So we usually restrict this to be only d plus 1. And when we consider this modification to be d plus 1, we just call this partition of the elements as an MA partition. Okay, this is where you will find this name on João Maia's thesis and in our paper also. So, okay, let's see what I want to say. So another thing is that we can take M will be large. M will be large, and will be chosen later. Later, because what happens that this M allow us to have good bounds on the good energy bounds for the cost of erasing a contour. So we choose accordingly with the interaction, and I will show you how to do this in a moment. And but the construction works for all M's, and also we will choose this A works. So if you consider the A equals 3D plus 1 over the minimum of alpha minus D and 1. Okay, so if you choose this, our bounds also work, but again, the construction, you can put any A basically on the construction. And what is happening at the interpretation over here is that what happens is that when alpha is closer to D, so especially when alpha is in this region right here, between D plus 1 and between D. Remember, this region right here is where the models are regular, so they can be, there is a thermodynamics defined, there is boundary conditions and a lot of things for deterministic systems with decay at least larger than D. And when you have something less than D plus 1, then this term starts to be in the minimum between these two, between 1 and this one. And then A starts to become larger. So what is happening is that the condition of separation of the contours is depending on how strong is your interaction. Because when alpha is closer to D, this means that the decay is slower, so the interaction between the components are stronger, and this means that in order to get good bounds, good energy estimates, you need to separate the sets even further, so even farther, let's say. So, oh, I don't know. Okay. So now what we want to do is to show that we can actually construct something that can be possibly non-trivial, okay, that satisfies both these conditions right here, A and B. And for this we use a multi-scale argument. To show the existence of something that may be possibly non-trivial. So first, we need to define some cubes. So define the what we call M cubes to be the following sets. So for any, they depend on X a point in ZD, okay? And then you define CMX as being the cube with side length it is 2 to the power m xy until 2 m power xy plus 1. Multiply it here, so we have this interval open on the right side, okay? But of course, this is an interval, the real line, so we make we only take the integer points on this interval, and then we make the product between 1 and D, okay? So this now is a subset of ZD. So this is a subset of ZD, okay? And what this is the following. So for instance, if I take X to be 0, then this cube is something like this. It starts right here and it goes until 2m minus 1, to the point 2m minus 1, okay? something similar here to m minus 1, and then I take all the integer points that are inside this cube right here. So the cube is something like this. And what is the advantage of something like this is that, for instance, if I take, this is the cube corresponding to 0, and if I take, for instance, 0 and 1, what I will get is a cube. I will get another cube. That contains all the points that are here on the open, sorry, so here I have the cube exactly like this. But if I take 0 and 1, what I get is that I will just walk a little bit here to m, and then I will take this cube over here as being cm01, okay? And also I can take something similar here. And remember, since we are in ZD, there is no point between these two. So what is happening to these cubes is that they are covering all of ZD. Okay, they are covering all ZD by translating X. Okay, you can cover all the ZD with these cubes, and this is it. So this is why this is important, because with this these cubes, they represent the scales in your problem. So for instance, if you take m equals to 0, then these cubes are just the points, okay? These are just the points. And then you are on the initial scale. So what we do to construct the contours using these cubes is that we must look what happens to the incorrect points of a configuration at each one of these scales right here. So, and how we do this? So, what we do is the following. So, for each L larger than 0, so we will define. So consider. So first, okay. Consider a finite subset of Z, and then for each L positive, we will define a graph. We define a graph GRL, where L is a positive constant, so we also consider some R larger than 1 fixed throughout all this construction. The R is important for the entropy estimates that we'll do another day. So then we have this graph is a pair, okay? These are L and ERL, and they are defined in the following way. So the vertices VRL are the cubes CRL, okay? So in the scale CRL, used in the cover, the minimal cover of A. Okay? So as I said, these cubes, they cover all of ZD, so you can use these cubes to cover a particular given set, and then you take a minimal cover, and of course this cover, this minimal cover in the sense that it uses the minimum amount of cubes. And also, this is unique because, as I showed you in the drawing, but you can check with the definition of the cubes, each one of these cubes is disjoint. So they discovered is unique. So you consider this, okay, and then you consider the edges between the vertices. So the edges between the cubes. So they will be pairs. Pair of cubes, such that the distance between them is less than m. Look here. Don't say anything wrong. Yeah. M to the power times 2 to the power ARL. So if the distance is less than this quantity right here, m times 2 ARL, then we will put an edge on each one of these cubes. So notice that this graph need not to be connected because, of course, since the set is arbitrary, then the distance can be much larger between each one of its components. So this graph is not necessarily connected. Okay, so now we have a graph for each one of the scales, and notice that since the set A is finite, this means that when I start increasing the scale indexed by L, so if I take L large, then eventually I will just need only one cube to cover A. So eventually all these graphs only have 1 point. They are all triple. So okay, so how do I use these graphs to construct the partition? So I need to do the following. I start. So first step. So we start with L equals to 0. So what we do in this case is we define the set B 0 as being all, let's say, not the connected components. So for this we define, before the first step I will need another definition. So since for each one of these graphs I have cubes, I can define another auxiliary set that I will call for each G subgraph of, let me ask, connected. So connected subgraph of GRL. Okay, I define the set A. We define the set A G. Okay, as being exactly the intersection of A with the cubes, with all the cubes CRL that compose that are inside the vertex set of G. So you consider the vertices of G. They are cubes. They cover A. They are part of a cover of A. They may not be everyone, So then I will take all the cubes and see exactly the subset of A that are covered by only the cubes that compose the vertices that are here and the vertices of G. So, okay, now we are ready to make the first step. So what is the first step? You look to the scale L equals to 0. And what you do is that you define a subset. In the following way. So, okay. You define P, P1, 1 for the first step. You consider it to be all the sets AG, okay, all the sets AG, such that G is a connected subgraph of GR, okay, so the first step, okay, so let me put it, the first step, GR, and then what you do, you need another restriction. You want that the volume of AG to be less than 2 to the power R d plus 1. Okay. V, remember, V is the volume, okay? V is the volume of this set of ZD that we defined before. So you take P1 to be all the subsets, okay? Where G is a connected subgraph of the scale, and the volume is small in some sense. It is small in that scale, okay? So what do you do next? Then you define A2 as being A minus the union of AG, okay, of AG for AG inside P1. So what happens is you subtract from A every component that you collected in this step. Then you get something A2. Then you get something A2. So what do you do next? So you take the next step, L2, the next step, the next step. Then you take the graph GR2, okay, that we defined here. But now, remember, to define this graph, we had to put another information right here that is something dependent on A, okay? So this is all dependent on A, and this makes sense for any finite set. So in the next step, the graph that we will take is constructed in the next scale, but using the set A2. This will be another graph, okay? And then you define P2 as being the sets A2G, such that G is a subgraph of GR2 connected, and its volume A2J is less than 2 to the power rd plus 1 times 2. Okay, so every time you increase the scale, you increase also the requirement that you put to extract a component. So in this way, you are always, in each one of the scales, you are always extracting the components that have a small number of points in its volume with respect to that scale. So again, we repeat the procedure. We define A3 as being A2 minus the union of as the union of A2G inside B2 AG2, and then we repeat again in the next scale. So for the nth scale, so continuing this procedure. What we are doing is that we have some set that comes from the last step, an, and we build a graph, grn, let's say. We build this graph, grn. Then we extract its connected components and define Pn as being all the AGNs where G is a connected subgraph, and we only extract them if their volume is small with respect to that scale. And then after we do this, then we define the next step as being the set in the next step as being the set in the last step minus the sets that I extracted already in this scale. Okay. So it's not hard to see that eventually this procedure stops, okay, because you get n very large and your set is it's finite, so eventually its volume, the remaining volume will be less than this quantity over here for some scale. So this means that this procedure stops eventually, and then we construct the partition, the MA partition, the candidate for an MA partition, as being the collection, the union, okay, of the Pn's n larger than 1 until some number n, where n is the step where an is eventually, okay. And again, this will happen because the cubes are getting bigger and bigger, and you are always extracting something from A, and the set is finite. So eventually it will get the empty set. So okay. Now we need to show why this satisfies both the conditions, okay. I will show first why it satisfies condition B. So why this satisfies condition B? So if I take two elements inside gamma, so if I take gamma 1 and gamma 2 inside gamma A, okay. So since I constructed them depending on these steps, then I know that there is n larger than m, okay, 2 steps that is larger than 1, such that gamma 1 will be equal to a g n, and gamma 2 will be a g prime, let's say, m. So what do I know about their distances? The distance between them. Gamma 1 and gamma 2. So since n is larger than m, this means that this component right here, the points that are contained in this component right here, they were extracted from in the construction before the points that are here. Okay. So I know that whatever, because the G and G prime are graphs that lives in different graphs in different scales. But I know that since the points that compose gamma 1 were in places that were not extracted were not extracted in the scale m, this means that their distance will be larger than okay, so one more thing before I say this. Since the points right here were extracted in another scale, okay, and for constructing this set right here, I take a graph that is connected. This means that any one of the points that are here, in whatever components they were in the scale m, they were not connected to this component right here, because again, this component is a connected component of the graph. So, and since by definition the edges are related to the distance, so the edges are related to this distance, it means that if they were not on the same connected component, this means that any point in gamma 1 must be at a distance from the points in gamma 2, at least this condition on the distance with respect to that scale. So this must be larger than m times 2 a r m. Okay. But okay, what this means is that if I divide this by d plus 1 and multiply it by d plus 1, what I get is m times 2 r m d plus 1. To some power a over d plus 1. But then again, since this component was subtracted in the scale m, I know that its volume is less than this, 2rm d plus 1. So this means that this quantity right here is actually larger, okay, than m times the volume of a m g prime, okay, to the power a d plus 1. And since I know that this component right here n is larger than m. I also know that the points in it were not subtracted in the last step. So this means that the volume, so this means that the volume of this of V of this one, since it is not it was not extracted in the last step, this means in the step M, this means that this is larger, okay? This is larger than 2Rm V plus 1. Because the points right here, whatever they were in its components, they were not extracted, so its volume must be large. So what this means is that this quantity is also larger than this. So in consequence, it's larger than this. So I can substitute this by the minimum value. Gamma 1, V, gamma 2, A, B plus 1. And again, I don't need to consider the other case because the analysis is it's similar. Okay. So now, okay, so the projector, yeah, show pictures, yeah. So what will happen is actually the following. In the first day of the conference, I will show the picture. So maybe I can show them the presentation. Because what is happening right now is the following. Tomorrow we will have the last class of the week. Tomorrow. And then Monday we have this construction again. Yeah, so maybe I guess. Yeah. Exactly. Like this is all to, let's say, it's a little bit hard because there is too much manipulation only on expressions, and there is little geometry in this construction right here. So if you want to see the idea of what is happening with pictures and colors, so you should come to the conference Monday, actually the whole week, come whole week. Yeah, yeah, at this, and then I will give another presentation with talking a little bit more of this construction. I will also show, because what happens in this construction is the following. This is a modification from a previous construction that we did, that João proposed this. Okay, that's João Maia. Many Joãos in Brazil, yeah, many Joãos in Brazil. And I will show in my talk a little bit of, it will be like, I will put this in a historical context, and I will explain why this is expected to be the right definition, and I will also show pictures of how this construction works. So okay, yeah. We don't know. Right now, yeah. What happens that I don't know, we don't know because we studied multi-scale arguments through another paper from the whole story started with this paper right here by, you can Fröhlich and Spencer. The story. Actually, this is not where the story started, but where I started to delve in this multi-scale things. One-dimensional. Just 1 second. Spencer, one-dimensional. Here. So Fröhlich and Spencer, the paper is the phase transition. The phase transition in the one-dimensional. The one-dimensional Ising model. With 1 over r squared interaction. Interaction energy. This is a paper from 1982 in Communications of Mathematical Physics. And this is a paper in one dimension where he constructed this kind of these contours using this type of multi-scale analysis. But the original paper is actually another one studying two-dimensional models, but with continuous spin, where they were studying something that maybe the physicists know as topological phase transitions, but there is a name, is BKT transition, related with Kosterlitz and Thouless transition, you know. And then they defined this multi-scale procedure to study these problems. We don't know if they had these ideas coming from something like renormalization, we don't know. But we use these multi-scale arguments for to study the multidimensional thing. About renormalization group, what we do know that is indeed a renormalization group is the work by Brickmo and Kupiani, but in the random field case. When you put a random magnetic field, then they use the renormalization group to conclude, to investigate phase transition. But we don't know if multi-scale have something to do with renormalization. I don't know. This is part of the story. We're studying right now this. Oh, yeah, exactly. So yeah. So what happened? So these arguments were made to define, to study very specific problems on phase transitions. Okay, and there was another. So they solved it. This was a conjecture that was open for many years to study this case right here, and this is connected to something that is called. If you look at that paper, there are some. They call the Kondo problem. The Kondo problem. This model was proposed actually by Philip Anderson first, related to another problem related with this physical phenomena, and they didn't know if this system right here had phase transition or not, and they solved this conjecture using the multi-scale argument. Okay, and there was another very important conjecture in another part of the theory related to Ising models, not long range, only nearest neighbor, but with a random magnetic field. So you have your Hamiltonian as being jxy, sigma x, sigma y, and then you add some hx, spatially dependent, but this is a random variable. This is a random variable, and usually you can think it as being a Gaussian, distributed as a Gaussian, okay, with mean 0 and a variance 1, okay, and then you put some parameter here. And what happened is that for this kind of systems right here, with around the variable, there was some heated discussions in the theory, because when they proposed this model, there was some physicists in IME. I don't remember if this is an Y. Do you remember? Y, yeah, in IME, that they said that by some arguments that are known as IME arguments, it's something they analyzed just a simple case and saw what is happening to the competition between the energy term and the random field case, and they predicted that there would be phase transition only when D was larger than 3, and they said something like this, and in the case D less than 2, the unique case. When you talk about the random field case, I will go back to this case right here. And after that, why there was a heated argument? It was because another two physicists, Parisi and Sorlas, they said that actually by using something that the physicists call dimensional reduction, maybe you already heard about this, and supersymmetry arguments, they said that the random field Ising model in D dimensions corresponds to an actual Ising model, but with dimension D minus 2. So what they were saying is that the magnetic field effectively decreases the dimension by 2. So as we saw, the Ising model with nearest neighbor interaction only have phase transition in D starting in dimension 2. So what this means is that if the random field behaves as D minus 2 Ising model, then this quantity should be larger than 2, and this implies that the system would have phase transition starting D equals to 4. And then there was a lot of discussions on this problem, because you see that these are very different predictions, okay? And then what happens is that in IME, in order to give their argument, what they said is something that they use something that we call isoperimetric inequality. We already use the isoperimetric inequality here. So and here we have some fancy quantum field theory arguments. So this question was solved by the mathematical physicists, and IME won in basically two different papers. Okay, in this first one we have the paper by Brickman, Kupiainen. It's a very famous paper. Let me take the name for you, where they introduced a rigorous version of the renormalization group. Brickman, Kupiainen, random. And the paper, if you want to take a look, this is a paper that is known as to be very hard to read and very technical. Phase transition in 3D, random field Ising model. And then in 1988, they solved this part of the problem, showing that there is phase transition in this case, but for nearest neighbor, for actually finite range, they claim that their argument works for any kind of contour, any geometrical object that you can call a contour. Suitable. We don't know what suitable means, but they say it's suitable. So, okay. And then there was this part of the problem, okay. Well, this already showed that Parisi was wrong, okay, because there is phase transition b equals to 3. So this already shows that Parisi was wrong. But this doesn't say nothing about this case right here. In the case of uniqueness, was solved by another two researchers, Ising and Ver. This case was solved by Ising and Ver in a paper called, it's easier to find, rounding effects of planchet randomness on first order transitions. This is a paper also in communications in mathematical physics from 1990. And here we don't have a renormalization group, okay? And you have other kinds of argument. This is already known as, this is known also as a very difficult result also. It's a very important result also. So what happened is that during many years, this was the only way to prove phase transition for the random field, the system with a random field. So what happened is that recently we were surfing on arXiv and we found a preprint giving let's say another argument for the phase transition in this case, an easier argument, more based, not based on the renormalization group, but based on the Pyros argument only, and also building in the work of other researchers. So, and this paper is actually published right now. Let me take this year. Here. So the name is long range. So the paper is by two Chinese researchers. So Jianding and Zhuang. So it's called long range order for random field Ising and Potts models. So the preprint was out in 2021, but the paper was published here first published online in 2023. Okay. First published in but it was out in a volume and everything in 2024. Actually, it's the first volume of a journal called Communications in Pure and Applied Mathematics, and it's on the first issue of the volume 77 this year, January, so 2024. And so they gave an argument not using renormalization group. Here you don't have renormalization group. You have other kinds of techniques that are difficult also. But what we did is the following. For these systems right here, the question is only for short ranges in models. So what happens to long ranges in systems? Because since the model have a magnetic field that can be negative, okay, because the mean is 0, so it must be negative, okay, for the mean to be 0. So you can the usual way that you infer phase transition using correlation inequalities is by Griffiths inequalities, and Griffiths inequalities doesn't hold if the field is negative. So if you have negative fields, so what you need to do is to show the phase transition by the old Pyros argument, the usual Pyros argument. So what we did is that we went, this work started in my thesis, so we are not trying to solve this problem. We didn't know this problem until 2000. We started work on this in 2021, let's say, yeah. So when I started studying this problem, I was interested only on phase transition with the decaying field, and then I read these techniques, multi-scale analysis techniques, and to build the contours and stuff like that. And then what happened is that João in 2021, he started to study, João Maia started to study this paper right here, and try to use the techniques of multi-scale techniques to construct the contours, and then prove phase transition for the random field with long-range interactions. Okay, and again, this avoids the renormalization group thing. So, and then he succeeded. But he succeeded, and he will give his talk at the conference also. His PhD defense will be Wednesday. It will be his PhD defense. So come here to see how he solved this problem. It was a very difficult problem. And then, but there is this restriction right here. Okay, there is this restriction right here. And what actually happens is that this restriction for uniqueness is only here because short-range models. Because if you have long-range models, this restriction doesn't apply. So for long-range models, the result for uniqueness is that alpha should be less than 3D. Oh, sorry, should be larger than 3D over 2 for D 1 or 2. Okay. Maybe I'm talking too much. No, I don't know. No, you can go. Okay. So, so the restriction for uniqueness that the decay should be larger than this if it is long range. And what we do know is that for D equals 1, there already are results for phase transition, the long range system, when alpha is close to 3.5. So if alpha is inside an interval containing, open, because in the one-dimensional case in 3 halves you have uniqueness also, then you have an interval right here of parameters where you have phase transition. Okay, so in alpha star is larger than 1. So this is not the optimal region of the parameters. So in d equals to 1, we already know that there is phase transition, and the argument again doesn't use a renormalization group. It uses also a Pyros argument. And our result doesn't use a renormalization group, uses a Pyros argument and Ding and Zhuang approach, but has this restriction, d being larger than 3. And then we have the remaining dimension, d equals to 2, that is completely open. We don't know. There is phase transition for the long range. So the question is, for d equals to 2, long range is in model with a random field, alpha between 2 and 3. Is there phase transition? So this is why we are studying renormalization group right now, to see if we put the information, because renormalization group doesn't depend on the dimension, right? So we actually don't understand why they had to put this restriction already. Yeah, exactly. Yeah, nobody tried to attack this problem because. Yeah. To try to do something. Yeah. Okay, and why they did in d equals to 1? Because in d equals to 1 there are multi-scaled contours by Fröhlich that were, of course, the argument is for interactions of type 1 over r squared, okay? But there were other researchers that extended this argument for other decays. So 1 over r squared is not necessary. You can have 1 over r to the power alpha, but you have some restriction on the alpha that you can make the argument. Okay? Yeah. The guy will be here next week also. So the guy that solved this problem, the random field in d equals to 1, he will be here. Okay, so yeah. So okay, we didn't advance too much today, but I will stop because I need to prepare my presentation. Okay, so